So first for electrostatics, we need to know our elementary charge. So the elementary charge is given on the back part of your equation sheets with the constants. It's the charge of an electron, E 1.6 times 10 to the negative 19th. And because you can only break down a molecule into electrons, then that is the smallest amount of charge possible. You cannot have any charge smaller than this. And because this is the smallest charge, that means that all other charges must be multiples of this. So I could have 1 electron, I could have 2 electrons, I could have 5 electrons, but I cannot have 1.67 electrons. So every possible charge in the world is a multiple of this charge right here. The conservation of charge, the total amount of charge in a closed system must stay the same. So like an example like this one, I could have -4 and -2. They could touch, they could exchange some electrons, but when they balance out to -3 and -3, I still have a total of -6. The similarities and differences, that's actually a question, so we'll talk through that. When two conductors touch, they share the charge. That total amount of charge is split evenly over the two. Opposite charge is going to attract, likes to repel, and then any charge with a neutral will attract. Neutral do nothing. It's only like a charge and a neutral will attract, so positive neutral or negative neutral will both attract each other. And then your new force in terms of your old force, so our force equation, so the electric force is the absolute value of Q over R squared. The absolute value means that if it's going from positive to a negative, that doesn't change the amount of force, the magnitude of the force. That would just change if it's like attracting or repelling or vice versa. So the reason I wrote the K blank Q over blank R squared is most times we're trying to find a new force in terms of the old force, so we don't really care if it's actually 5 newtons. We just want to know how many times bigger or smaller the force is. So we want to know how many times bigger or smaller our charges are, or our distances. So if I double the charge, that would be twice the force. If I double the distance, that would be 1/4 the force, because R is squared and it's on the bottom. Alright, our need to knows for electricity. So these two laws, super important, the Kirchhoff's laws for voltage and current. The sum of voltages in a closed loop adds up to 0. So an example of this would be like if I have a series circuit, I have a total voltage, and then each resistor has its own voltage drop, V1, V2, V3. So what this is saying is V total, so I'm going to make this positive because battery provides the voltage, and then that voltage is like dissipated or used up right here. So I'm going to say minus, or dropped, the voltage drop of 1, minus the voltage drop of 2, minus the voltage drop of 3, equals 0. That's also the same as saying, okay, these 3 voltage drops together equal how much voltage I started with the beginning, V total. And that's because it's a closed loop. Now, if we look at a parallel circuit, so this would be V total, this would also be V total, this would also be V total. Here, I would not add up V totals to get to V total. Remember, the law says in a closed loop, so if you just pick one loop, this one around like this is saying, okay, I start with V total, and then I drop V total, I get 0 in this closed loop. Or you could say, look at this closed loop. I start with V total, and then I drop V total, that would also be 0. So I have 3 different loops, all starting with V total and all dropping V total. So all of these loops have a sum of voltages of 0. Alright, the sum of the current into a junction equals the sum of current out of a junction. So for a series, that's really easy because I'm saying, okay, I have the total current out of the battery. There's no junctions, there's corners, but there's no junctions, right? And then, okay, what's coming back into the battery? Well, what's coming back in is I total. So the total that's coming out is equal to the total that's coming back in. Now for parallel, this looks a little different because I don't have the same current throughout, it actually splits. So this is saying, okay, I've got total current coming out right here. And then, so if this red right here is my total current, what happens when it comes here is it's going to split. So I've got like this current right here, and it's going to split. I don't know exactly what the numbers are, because it depends on like the resistances here, but some is going to go here and some is going to go here. What this is saying, this rule is saying, is that these two, the sum of what's coming out equals the total that's coming in. So here, the I of the pink marker plus I of the yellow have to add up to the I total that was coming into the junction. And then here, so you could say at this one, get some, oh no, I'm running out of colors, that's okay. This is my pencil current, and this is my black current, or that looks more like blue. So this is saying that my I of the pencil plus my I of like the blue marker adds up to the total of the pink one. And then here, that means that the blue and the pencil come back together, so I get my pink back. And then here, my pink and my yellow come back together, so I get my red pen back. So my yellow plus my pink add back up to the red, or the total. And then in this part, we said the pencil and like the pencil and the blue add up to the pink. Oh, those don't look like words. Anyway, hopefully you get the idea is that the current into a junction has to equal the total current out, and the total current into the junction has to equal the total current out. So here. And then your overall, you could say like these two individuals add to this total, these two add up to this total. Or you could say the yellow, so like I of the yellow plus I of the pencil plus I of the blue adds up to my total. Probably would have been easier if I called this I1, I2, I3. Add up to your I total. Alright, cool. The potential difference, that's a difference in electrical potential energy from one point to another point, so it's always across, so like from here to here, that's just the voltage of the battery. From here to here, that's the voltage drop of the first resistor. From here to here, that's the voltage drop of the third resistor. From here to here, that's the voltage drop of the 1 and the 2 resistor. If we're talking about a parallel circuit, from here to here, that's the voltage of the battery. From here to here, that's the voltage of the battery. From here to here, that's still the voltage of the battery, because you're literally finding the voltage of the battery, just extend the wires. Now, if you were to put a resistor right here, this would be the voltage of the battery. This would not be the voltage of the battery, because you're dropping some along this branch. Your current, that's the rate the charge is flowing through a part of the circuit. Power, that is the rate that the energy is transferred, or you could say the rate that it's delivered from the battery, the rate that electrical energy is used up by resistors. Important thing there is it's the rate, so how much energy you're using per second. Open circuit is like if I were to, for whatever reason, I were to unscrew this resistor right here, then this is now an open loop, so there would be no current flowing. You can erase this current right here. That would be an open loop right here, but as long as these are closed loops, current will still be flowing in these closed loops. A short circuit would be, like if I unscrew this, now there's no current because there's only one loop, so there's no current at all. Short circuit would be like if I had something like a switch like this, and if I were to close this switch right here, now current, instead of going through all the resistors, would only go through, it would skip over the first and only go through the second and third resistor. That would be like shorting or providing a shortcut over the first resistor. And, okay, similarities and differences between the electrical force and the gravitational force. So if you look, so I'm just going to do the equation real quick. Q over R squared, and gravitational was G-M-M over R squared. And those are Q is like the top right here under electricity, and gravity is down here by the bottom. Absolute value. So one of the key differences is that Fg is always going to be an attractive force, so always attracts, whereas Fe can repel or attract. It just depends on if they're like charges or opposite charges. But Fg will always attract. So that's one difference. Another difference is that, so this one depends on charge, this one depends on mass, and then they both have the constants, but if you look at the constant, so for K is 9 times 10 to the 9th, whereas G is 6.67 times 10 to the negative 11th. So this is 10 times to the 18th difference between them, which is like 18 zeros difference between them. So K is a much bigger constant. So another difference is K is a much bigger constant than G. So a pretty safe rule, it won't always be true, but pretty safe rule is that your electric force is, in general, a much stronger force than your gravitational. The exception would be like if something doesn't have a charge, but it does have mass and it has gravity but no electric. But just in general, because K is a much, much bigger constant, you can say this force in general is a greater force or stronger force than gravitational. And then the main similarities, the main one that I wanted you to see is that they're both depend on the 1 over r squared. So the similarity is that they both depend on 1 over r squared. So the farther away you get, the smaller the force for both of these, and then the closer, the stronger the force. And it's not just 1 over r, it's 1 over r squared, so it's actually like a big dependence on r, more so than the dependence on charge or mass. All right, number 2, a scientist is doing an experiment and finds that the charge of a particle is this much, give or take this much. Is this reasonable? So let's think about whether an amount of charge is reasonable or not. Is it a multiple of the elementary charge? So I'm going to take my 5.3 times 10 to the negative 19th. I'm going to divide it by 1.6. That's going to get me 3.31 elementary charges, or electrons. Actually, protons, because this is a positive. I cannot get 3.31, but let's look. This is saying give or take 0.05. So the other way to do this is we could divide this. So this is saying 3.31 electrons plus or minus, and we can divide, actually do this one, so we can divide the 0.05, 0.05 e negative 19 divided by the 1.6. Let's see, let's see, this would be plus or minus 0.03 elementary charge. So what I've done is I've taken this statement, which is in coulombs, and I just put it into elementary charges, because I can't really tell just looking at coulombs if it's reasonable, but I can tell looking at elementary charges. So this is saying 3.31 elementary charges, give or take 0.03 of an electron, or of an elementary charge. So this is not possible, because I can't have 0.31, and I can't have 0.34 or 0.32 or 0.29 of an electron either. So no, because it's not a multiple, not a whole number multiple of elementary charge. Even when you take into account the margin of error, it's still not a multiple. Now the next one, this right here is 3.9675, I think, elementary charges. 875 elementary charges. So you're looking at like, well, I can't have 0.96875 in an elementary charge, but let's look at our margin of error. Because this isn't saying it's exactly this. It's saying it's this, give or take a little bit. So let's see what our give or take is. 0.1 divided, or like e, whatever, divided by the 1.6. This is saying plus or minus 0.0625 of an electron. So yeah, and you don't have to actually add 0.0625, right? It's give or take within. So if I add just 0.03 something, that gets me to 4, so that's within my margin of error. So yes, this is reasonable, because this is 4 electrons when you take into account the error, the plus or minus, whatever your give or take error is. All right, number 4, object A has a charge of positive 4 microcoulombs. The micro, this little mu, doesn't stand for coefficient of friction. It is its own prefix, so the same way like centi millimeters, you can have micro, which is 10 to the negative 6. Just letting you know what that is. So that's A, and then B is plus 10 microcoulombs, and they are a distance 2 meters apart, and they have a force F between them. And then object C has a charge of 3, and it is going to stay with object A, but B is removed and replaced with the negative 3 microcoulombs, and now they are 6 meters apart. So I want to know what my new force is in terms of F. So here, because I'm not trying to find like an actual number, I could plug in K times charge over 6 squared. That's going to give me the actual force and not how it relates to the original force. So what I'm going to do is like a what would happen. So K, what Q over what R squared. So I started with A. Well, A was 4 microcoulombs, and it's still 4 microcoulombs. That's just 1 of the original charge. So 1, nothing happened. Here, it was 10, and now it's -3. We don't really care about the negative because it's going to get absolute valued anyway. It just changes that these at first were repel and now they're attracting, which doesn't change like the magnitude of the force, so we don't really care about the negative sign. But it was 10 microcoulombs, and now it's 3, so that means you're multiplying by 3 and dividing by 10. You could think about it as like new over old is your scale factor, or I just think about I had 10, I don't want 10 anymore, I want 3, so I'm going to multiply by 3, that's 30, divide the 10 out, and that gives me 3 again. So I have 3 tenths, the original charge, and then it was 2 and now it's 6, so I have 3 times the distance. So now I'm just looking for factors of change. 1 doesn't matter, k stayed the same, the q's like factor out, the r squared factors out, it's just the 3 over 10 over the 3 squared, which is 9. Put that in your calculator, math enter, that's 1/30th of the force. And we knew it was going to be smaller because I have less charge and farther apart, so I just did 2 things that make it smaller. Right, number 5, so we have -9q and positive q, and they are distance d apart, and now they're touched together and they're separated, so now still a distance d apart, but when they're touched together, the -9 plus the +1, this isn't a 0, it's a +1, so that's a total of -8, so then they each have -4 on, -4q, -4q. So 2 ways to do it. I think most people do the, okay, this is k, 9q, q over d squared, and now this is k, -4q, well, we don't care about the negatives. 4q over d squared, so this is 9k q squared over d squared, and this is 16k q squared over d squared. Well, it was 9, now it's 16, so that's 16/9 of the original force. That's one way to do it, or you could do it very similar to what we did up here. Okay, I had 9, but now I have 4, so now that's 4/9 the charge. I had 1, but now I have 4, so that's just 4 times the charge. Nothing happened to d, so that's just like 1d squared. 4 times 4 over 9, well, that gives me 16 over 9, the old force as well. Either way works. So we've got R, which is +3 microcoulombs, 1 meter from E, which is +7 microcoulombs. They have a force F between them. R is removed, and X, which is -4 microcoulombs, is placed 2 meters away, and it's still next to E, which is still +7. So I'm going to do like the what would happen. So this charge changed. It went from 3 to 4, so that's 4/3 the original charge. This one stayed the same, so that's still 1q. And then the distance went from 1 to 2, so that's twice the radius. So if I'm just looking at like the factors that changed by, I have 4/3 the original on top, and then 4 because the 2 gets squared, so that leaves me with 1/3 the original force. Number 7, we've got -4 and -6q, and they are distance d apart. When they touch, that's a total of 10, so it'll be -5q, -5q. So 2 ways you can do it. You could say, okay, my charge changed. This is now 5/4 the original charge. This is now 5/6 the original charge over same distance squared, so like 1d squared. That gives me 25 over 24, the old force. So tiny bit greater. Or you could have said, okay, this is 4 times 6, which is 24 kq squared over d squared. This is 5 times 5, which is 25 kq squared over d squared. Well, if it was 24 and now it's 25, it's 25 over 24 times the old force. Either way it works. Right, into circuits. So we have potential difference in current for each resistor in a circuit, and we want to know which one of these represents the correct circuit. So I looked at potential difference. This is my V total right here of the battery, and I noticed that none of my resistors have the total voltage. So that crosses off this one because this should have 4 volts if this is your battery. If this is your battery right here, then R3 should have 4 volts. So by process of elimination, this is the correct one. But we can also look at, okay, These two have the same voltage, which makes sense because those two are in parallel with each other, and it does not have the same as the battery because this is going to drop some before it gets here. Remember when we talked about like from 1 point to 1 point? So if this has 4 volts right here, if I go through here, nothing's changed, but if I go along here, I'm dropping some, so now the difference is not 4 anymore, it's less than 4 because I ate up some of that voltage. We could also think about current. So this is my I total, and it's saying that this resistor right here has the total current going through it, which is absolutely true because coming out of the battery, it hasn't split up, it hasn't split up, this is the total, this is the total, until it gets here, and this is where it like splits into 2 different currents. And then it's going to come back, and then this is going to be I total again. So this has the total current, and then these 2 currents add up, so these 2 add to I total. So those are all the reasons why we knew this one is matching. All right, number 4, when one of the 2 ohm resistors is removed, so I'm going to take this out, what happens to the potential difference across the 4 ohm? Well, the potential difference across the 4 ohm is just the current times the resistance. The resistance is still the 4 ohm, so it's just like has my current changed. If I take out a resistor, I've changed the equivalent resistance of the circuit, so I've changed the total current through the circuit, which means I've changed the total current through R, or through the 4. So it is going to change, so that's how we know it's not A. Now to find out how much it's increasing or even decreasing by, we're going to just have to do the math. So 1 over 2 plus 1 over 2, 1 over that is going to get me 1 ohm. And then the 4, this one would have an R total of 5 then. If it has a V total of 10, then that means that my total current is 2 amps. So I've got 2 amps coming out right here, and then it's going to split here, so I don't know those, but it comes back together, which means that this one has 2 amps. And if I have the current and the voltage right here, or sorry, the resistance here, I can find that this is 8 volts. And then because this is my total voltage of 10, and this one drops right here, it drops 8, that means that these 2 have to drop 2 volts because they have to, in one closed loop, they have to add up to the total. And these 2 are in parallel, so they each get the 2. It's not splitting the voltage, they both get the total voltage. Alright, so I know the original potential difference of the 4 volts. So at first it was 8 volts. Oops, it was 8 volts. And then now I need to find out what the new one would be. So if I have 10 ohms, but I take out a 2 ohm, that's basically just saying cover this up. Now it's just a series circuit with the 2 and the 4. So 2, 4 like this, 2 ohms, 4 ohms. So then 10 volts, this is a total resistance of 6, so that means 10 divided by 6, that's a total current of 1.67? Yeah, I think so. So then to find this voltage, if this has 1.67, you just multiply, you get 6.67 volts. So it was 8 volts, and now it is 6.67 volts. That means it's decreased, so we can cross off these, and then you just literally subtract. So this one minus this one, it decreases not by 0.33, but by 1.33, so E. 10, the current through the battery, so that's just saying total current. So to find total current, you need to know total resistance. So I cannot add 5 and 6 because they do not share the same current because current is splitting right here. But I can put 3 and 6 together because these 2 are in parallel. So I'll do the 1 over 3 plus the 1 over 6. That's going to give me, I think it gives me 2. Let me check. Yep, this just becomes 2, so it's like a 5 and a 2 ohm. Oops, ignore that. My battery. This is a 5 ohm, this is my 2 ohm, so that means that our total is 7 ohms. And if this is my total voltage right here, that means my total current is 2 amps. So I through the battery is just the total current, 2 amps. The current through the 6 ohm resistor, so it's very tempting to be like, oh, 14 divided by 6, that gets me my current. But that's only the case if this had a voltage of 14. Which it doesn't, because this right here, the battery from one side of the battery to the other is 14. If I go through the wire, yeah, that hasn't changed. This is a voltage of 14, but as soon as I cross this resistor, I'm changing the voltage. Some of it's getting eaten up or dissipated. So then here, this is a different voltage than 14. It's less. So I need to find out how much of this voltage was used up. Well, my total current is 2 amps, so the current coming out of the battery is 2 amps. If I follow this path, it's still 2 amps, it hasn't split, it's still 2 amps, it only splits right here, so this means that I have the total current through this 5 ohm resistor. So 5 ohms with 2 amps, this is a voltage drop of 10. So if this is 14 and I drop 10, then from here to here, this is 4 volts. From here to here, this is 4 volts. They're in parallel, so they all have the total voltage that's left, the 4 volts. So then to find the current through the 6 ohm resistor, well, current is voltage over resistance. This specific resistor has a voltage of 4 volts over a resistance of 6, so the current is 0.67 amps. Number 12, what is the potential difference across the resistor R? Well, if you look right here, I've got current and resistance, so I can say that this has a voltage drop. So voltage is I times R, 0.5 times 50. This has a voltage drop of 25 volts. And that's specifically the first voltage drop. I want to know what my second voltage drop is. Well, I know that the V total is 120 volts, so if I'm providing 120 volts and I drop 25, how much do you have to drop to be back at 0? Well, you just subtract 120 minus the 25. That gives me the second voltage drop is 95 volts. Okay, cool. The sum of resistances R1 and R2 make 10 ohms. So I'm just going to redraw this. 10 ohms. This is 5 ohms with 4 amps. And then I also was given a current right here. Well, I have a resistance and I have a current, so this gives me a voltage of 20 volts. And then this is in parallel with this one, so this has 20 volts, and this one has 20 volts right here. I want to find the current through the left branch, so I want to know what is this current right here. This is ohms, by the way. So 2 ways to find it. I think most people do the find R total, so 1 over 10 plus 1 over 5 to get R total. That gives me an R total of 3.33 ohms, and then V total equals I total R total, or sorry, I'll just do it. The I total is the total voltage 20 divided by total resistance 3.33, so that gives me a total current of 6 amps. Now the trick here is that you just found the total current, not what I asked for. What I have is total current 6 amps coming out of the battery. I know that 4 amps is going to go in this route, so what's left is the 2 amps to go to the first one. The other way to do it is you can know that this one has a combined resistance of 10 ohms, and has a total voltage across it of 20 volts, so you could just divide to get the 2 amps. I think it's probably a little bit more intuitive to get your R total. This is 6 amps, and then if there's 4 here, that means there's 2 left, because the total amount of current into a junction has to be equal to the total amount out. So 4 and 6 equal the total 6 in. Or sorry, 2 and 4 equal the total of 6 in. Alright, number 14, identical bulbs. These 4 are connected to a battery as shown. Rank the potential difference across each bulb from greatest to least. So let's start with B has to equal C, and we know that these are equal because they're in parallel with one another. So that means that the potential difference from this point to this point is equal to the potential difference from this point to this point, because they're just connected by a wire. But it is not the voltage of the battery because it's dropping some on its way to those 2 points. Alright, and then A and D should be equal. A equals D because these 2 are in series with one another, so they're in series, which means they have the same current through each bulb. And they each have the same resistance, so if V equals IR, and this is the same and this is the same, that means you'll have the same, same voltage drop. Sorry, this is terrible handwriting right now. Alright, and then now it's just figuring out which one is greater, and we should say that A and D have a greater potential difference than B and C, so AD is more than BC because A and D have the total current. B and C have half the I total because the current splits between them. So if you imagine, like, let's say this comes out with like 4 amps right here. This would have 4 amps times the resistance R, get some voltage. That 4 amps is going to continue, and then it splits in half. So this one only gets 2 amps with the exact same voltage, or sorry, exact same resistance, But with less current, that's going to be a smaller voltage drop for each of these, and then it comes back together. This also gets the 4 amps with the same resistance, so it's that big voltage that's equal to the original. And then if we were to add up this voltage plus one of these plus this one, add up to the total voltage. All right, B, this bulb is now unscrewed, leaving its branch open, so now it is just A, C, and D. That's a terrible drawing. Now we're going to rate the potential difference across each bulb from greatest to least, so you should be saying that A equals C equals D because they are all in series. They each have the same current, the I total, with the same resistance, so that means the same V, because delta V equals IR, so if these two are the same, then the third has to be the same. Okay, now C is asking what happened to that potential difference across bulb A when it was unscrewed. So what we said is that these three bulbs all share the same potential difference. Whatever your voltage, original battery voltage is, it's now split exactly equally between these three bulbs. But that we didn't say that this is the same as it originally was. In fact, it's actually going to be different because the voltage drop across A is just the current through A times the resistance of A. We know the resistance has stayed the same, but we do not know that the total current in the circuit has stayed the same. Now, a lot of people get a little tricked up on the, wait, but current is the same in a series circuit. I agree. Within a series circuit, this is the same current. This guy and this guy and this guy and the battery all have the same current. That doesn't mean it cannot change when I change the circuit. It doesn't have the same total current as this circuit. That's different. So let's think about when we took out the bulb, we took out a resistor in parallel. Now they're all in series. So when we take out something in parallel, we have more of a R total. So you have more equivalent resistance, because you took out a bulb in parallel. And when you add them in parallel, you get, it's weird, but the more resistors in parallel, the less R total you get. So if I take out one in parallel, I get more R total. And because I have more R total with the same total voltage, you have less total current. So then the current through A is less than before, so that means that you have less of a potential difference now. And your reasoning is you have less of a potential difference because you have less total current through the circuit because you have more total resistance in the circuit. If you were unsure, what you could have done is you could have made resistances. They're all identical, so it doesn't matter what resistance you use as long as it's the same everywhere. So 1 over 1 plus 1 over 1, 1 over that gives you 0.5. So this one has an R total of 2.5. This one has an R total of 3 ohms. So here, and you can use numbers like that, so you could say, if you need to explain the why there's more R total, for example, if each resistor is 1 ohm, R total is 2.5 at first, and R total equals 3 when, because it's just 1, 1, and 1, when B is unscrewed. Okay. What happened to the potential difference across bulb C when B was unscrewed? So the way I thought about this is, okay, we know that both A and D, they had the same amount before. Now they're equal to each other, and we just said A is less, so we know that D is less as well. So A and D have less potential difference than before. And you know that all 3 voltages added to the V total of the battery in both cases. So if you're saying voltage 1 plus voltage 2 plus voltage 3 add up to the total, and you're still saying that I'll call it VA, VB, or VC, and VD, these 3 voltages still add up to the same total, but these are less than before, it means the third thing you're adding in must be greater. So all 3 voltages still add up to the V total, that means that the potential difference across C must be greater. So an example, like if you're like, wait, why does that? An example would be like, okay, V total is 30 volts, right? And we know V1 plus V2 plus V3 have to add up to V total. So at first, that could be like, I don't know, 12, 12, add up to 30, what's left? I can do this, 6? Yeah, 6. Whereas now you're saying, oh, that's less. Now it's 10, this one's 10. Well, they still have to add up to the same amount, so this one has to be greater to make up for like the 2 and the 2 you just lost. I just made up numbers here, but this is what, like, just giving an example, like, okay, if these add up to the total, but you just decrease these and they still add up to the same total, this one has to be greater. Or you could actually do the math, make up some voltage, as long as you keep it the same here, use the R total, find what each voltage drop would be. That would also be good reasoning. Alright, number 15, a resistor of resistance R and a resistor of resistance 2R are placed in series. At time t, the resistor R has dissipated or used up an amount of energy E. How much energy has the 2 ohm resistor dissipated at time t? So how much energy each has used up? It's tempting to think through voltage, but it's actually not just the voltage, because voltage is how much energy, but I'm asking in reference to the amount of time. So here we're going to be looking at power, because power tells me the rate that energy is used up. So I'm going to find, so let's say this has a current I. I don't know what it is, but let's call it I. And I can just call it I because I know it's the same throughout. So this has a current I, and this one has a current I as well. Voltage is V times IR, so this one has a voltage of IR. This one has a voltage of I times 2R. So, and let's call this V total so that you're not like, wait, what? Because it's not the same. So this one has a V equals IR, V equals I2R. Now your power is just I times R, voltage, I times voltage. So they have the same current, and then this one has twice the voltage. So here, this one is going to, if we said this one has a power P, this one has a power 2P. And why? It's easier than like using all the letters. So 2R has 2 times the power because they have the same I, but 2 times the voltage because V equals I2R, so we have twice the voltage. Alright, so once we know that this one has twice the power, that means that it's using up, so it uses 2 times the amount of energy per second. So if the first one has used an energy E in that amount of time, then they would have used twice as much energy in that amount of time, so 2E. And you can't always say, like, oh, more resistance, that's more, like, power. Because that's actually not true. If you have it in parallel, here, oh, that's bad. You have 2R and R. Here, if I have the exact same voltage, because it's in parallel, that means this one has less current with the same voltage would be less power. So don't just say the whatever more R is more power, because that's not necessarily true. It's whether it has more voltage or more current. Here, current is the same as a greater voltage. All right, 16. You know nothing about this circuit except for 2 ohms and 3 ohms. I don't know any potential differences. I don't know the battery's voltage. I don't know any currents, and I want to know what information would I need in order to find this missing resistance missing resistance R, and there's 2 answers. Now it's really tempting for people to say like, oh, I just need to know like the UV, which is just the voltage of the battery. If I know UV, I would know the total voltage, and I would know this current right here, and I would know that the total voltage across this branch is whatever I just found. But that doesn't give me the missing resistance, because I don't know what this current is, I don't know what the total current is, so it's not like I could subtract. And if I don't know this voltage, then I can't find the missing voltage or the missing current, etc. or missing resistance. So just one thing is not going to be enough, because it would only give me the voltage and this current, not related to the total or the missing branch. If you look from S to T and U to V, that's actually giving me the exact same answer, or the exact same information over and over, because this voltage is this voltage right here, so that's not going to be helpful, because that's just saying the voltage of the battery, which isn't enough. S to T and X to Y. So S to T and X to Y. So let's think through. This would give me V total, so you would know V total, which means you would also know the V of the first branch, which means you could then find current through the first branch right here. And then if you knew X to Y, then you would know this missing voltage right here, which if you knew the total, then you could subtract to find this missing voltage, which means you could find this current. And then this shares the same current, so if you know this voltage and this current, you can divide to get R total. So yes, B would work. Now C from U to V, so that's again getting the total voltage, and W to X. Yep, this is pretty much the exact same thing. The only difference here is I am giving the total and then this missing potential, which I can get this one really easily, because if this is 5 volts and this is, I don't know, 4 volts, and this missing one is 1, because you know they add up. So this is essentially the same thing, so C would also work. Now S to T and X to Y, so the reason this doesn't work is because it doesn't help me distinguish between the 3 and the R. I already know what this voltage is, right? This voltage is the UV, is the UT, so that's not going to help me at all. Now, so a lot of this was kind of probably process of elimination. Well, it's not just one, and then these two are the exact same thing, these two are the exact same thing. So I'm going to talk about what you would use in the steps you would take with those two pieces of information to find the missing resistance. So for B, so this is answer choice B, and this is answer choice C. So for part B, we said the voltage from S to T. So that means V from S to T is V total, and it's also the voltage drop across UV. So you can use this to find the current in the UV. Do we need to find the current? I don't know. We don't need to find this current actually. But we do need to know what that voltage is. So don't worry about that part. Ignore that. We don't need to know this current. And then this is where we actually need to know the current from X to Y. If you know X to Y, so X to Y, you're going to subtract from V total to find the voltage drop from W to X. And then you can use this to find the current through the 3 ohm resistor. So this would be saying let's make up a number. Let's say this is 5 volts, and then I find out that X to Y is 2 volts. Well, if this is 2 volts and this is 5 volts, well, this has to be 3 volts. So you would subtract to find the voltage drop here. And then once you know this voltage drop, well, we know this resistance, so we would use that to find the current. And then once you have that current, that is the I through your missing resistor R, so you can use the R is I divided by V, V equals V divided by R to get your missing R. So I wrote that really messy, so let me just talk through it again. This is my total battery voltage, which I need, because if I find just one part, I can subtract and find the other one. Once I have the other one, well, I know one voltage with its resistor right here, so I can find this current. Once I know this current, well, this is the exact same current, so then I can use V equals IR with this current and this voltage to find this resistance. All right, the second answer, so very similar. Here you're finding U to V, so the voltage from U to V is just V total. And then from X to Y, or no, W to X, yeah. So you use the voltage from W to X with the 3 ohms to find the I through the 3 ohms. That is your I through R, because they're in series with one another. Obviously, these two are in parallel with the 3 ohm, but they're in series with one another. They share the same current. And then now I need to know what my missing voltage across R is. So you're going to subtract the total voltage minus the voltage of WX to find the voltage across XY, the voltage across the R resistor. And then you use the I you found to find the missing R. So super similar, just working slightly backwards. Here I have the voltage and I have total voltage and I have this voltage, so I can find this current, which is then this current. To find this voltage, well, it's just the total minus this one, and then once I know this resistor's voltage and current, I can find R. Alright, 17. The sum of resistances of 1 and 2 are 12 ohms. This is like a 3 and a 12 ohm. Wow, these are getting worse and worse. And then this right here is 2 amps. So then I can find the total voltage, because this voltage drop is 6 volts, which is also this voltage drop. The current through the battery, so I would find our total. That gives me a total resistance of 4? No, 2.4. And then I'm looking for I total, that's V total over R total. Total voltage is 6 volts over 2.4, so that gives me the total current, or the current through the battery is 2.5 amps. Now if I ask what the current through right here is, well, 2.5 is my total coming out of the battery. 2 going this way, that leaves 0.5 going this way. Which also is what you would get if you use the 6 volts with the 12 ohms, you would get 0.5 as well. Alright, battery has an internal resistance. This is just saying, like, each battery, we haven't talked about this, but most batteries have their own little resistance built in, not like intentionally built in, it just happens because things have resistance. So I have these two, and then this little resistance that goes with the battery. It says that R1 is the biggest resistance. This is the biggest R, this is like the medium R, and this is the least R because it's pretty small. Most times we just ignore the internal resistance of a battery because it's so small. And none of the resistors are equal, and I want to know which of the following about their currents are true. So I'm going to call I3 the I total because that's the total current coming out of the battery, and I know that when it comes right here, it's splitting into 2. So if we're using Kirchhoff's law that the current into a junction must equal the total current out of the junction, that means that these two, I1 plus I2, have to add up to my total current, which is just I3. So current 1, current 2 add up to I3. That's true, because I only have 2 separate currents that then come back together to the total current, which is the current through the battery, I3. And then I'm going to look at like size of current. So I3 is definitely the biggest current because the 2 add together to get to that current. So I3 is the greatest current. So just by process of elimination, I can cross out these ones and I'm left with 3, that I is the biggest. But the reason that I2 is greater than I1 is because these two have the same voltage drop. So V1 and V2 are the same. It's just going to be like the voltage of this whole battery part right here. Why they have different currents is because it tells me that R1 has a greater resistance. So if it has a greater resistance, R1 is going to have the least current. So biggest resistance with the same voltage will be the least current. So A and E. Okay, I'll do the third page with like free response tomorrow.